I'm Dave Breckle, Panel Solutions Specialist for Omron Electronics in the UK. Welcome to this panel TechTalk. In the next couple of minutes, we're going to talk about considerations when using relays above 2,000 metres. Although Omron doesn't specify any altitudes in their datasheet, for the figures we generally assume that our product's going to be used at an altitude below 2,000 metres, or 6,500 feet. Now this isn't really an issue for us here in the UK, because our highest mountain is Ben Nevis at 1,345. But there are a number of countries around the world where you will find a higher elevation, and including Europe, such as China, Peru, Nepal, and a lot of applications you may be asked to build for, such as mining and leisure activities. Why is this important? Well, the higher your altitude you go to, the lower the air density is going to be, and also you'll have a lower heat transfer capacity. This can have an effect on a number of electrical items, such as motors, thermal overloads, switchgear, contactors, and relays. Essentially, the higher you go, in terms of altitude, the more we have to look at derating the product. This is governed by a series of laws called Paschen's law. In the 19th century, a German physicist called Friedrich Paschen did a series of experiments where he placed two electrodes 1 centimetre apart and varied the atmospheric pressure. He placed them in atmospheres between sea level and 260,000 feet, and at regular intervals he measured the voltage that was required for an arc to form across the terminals. From this experiment, he created a series of graphs, which we can see here from Paschen's law. And essentially, as the air pressure, or in our case, the altitude increases, the voltage required for it to break down an arc across reduces. So essentially, at a higher altitude, you need a wider clearance gap than you would, for example, at sea level. Now, spontaneous arcing isn't so much of an issue for us with relays. We're probably a little bit more concerned with breaking the arc once the relay is switching at load. When an arc forms, say between the two poles of the relay, what we're actually seeing is a series of electrons passing through ionised air, what we call a Townsend discharge, or a Townsend avalanche. Essentially, you've got an anode and a cathode. The electron starts to move across, will collide with another atom, and knocks an electron off it. This will then hit another atom, which causes another electron to become free, and it multiplies out into this avalanche. Eventually, once the distance has reached a certain distance, the arc will break down. There won't be enough speed. When we have a high altitude, these atoms are actually further apart, so the electrons can actually pick up more speed, which involves a longer arc. It will take longer to break. This is an issue really for us with relays, primarily because the fixed contacts inside it are a set length. So at a higher altitude, what you may find is that the arc will last longer, or it may not break at all if you're running at full load. The way to get around this is to derate the relay. So essentially, what we have to do there is derate the switching current and the ambient temperature. Now, IEC 60064-1 is a standard that lists a number of helpful tables. You can see the one I've put up here is the altitude correction in terms of distance for manufacturing clearances. But they have a series of tables in there which will also cover you for loads and for temperatures as well. Finally, as well as derating the relay itself, perhaps consider fitting surge arresters in the circuits as well. And that will protect against transient voltages and limit any sort of tolerated overvoltages in the circuits as well. So, these are the considerations when using relays above 2,000 metres.